Good day everyone, I am Mark Deyle Sanchez and this time I'll be discussing Lesson 7 which consists of two methods of solving non-homogeneous linear equation. First is the methods of undetermined coefficients. Second is the methods of variation of parameters using WRONSKIAN. In methods of undetermined coefficients, we must consider the form ay double prime plus by prime plus cy equals g of x, where g of x is not equal to 0. Then the general solution is y equals yc plus yp, where yc is the complementary equation and yp is the particular solution. Example number 1. Determine a particular solution to y double prime minus 4y prime minus 12y equals 3e raised to 5t. Our given is y double prime minus 4y prime minus 12y equals 3e raised to 5t. Now let's proceed with finding a particular solution. As mentioned prior to the start of this example, we need to make a guess as to the form of a particular solution to this dE. Since g of t is an exponential, and we know that exponentials disappear in the differentiation process, it seems that a likely form of the particular solution would be yp of t equals ae raised to 5t. All that we need to do is to do a couple of derivatives. Plugging this into the differential equation, y double prime minus 4y prime minus 12y equals 3e 5t, or 3e raised to 5t, and see if we can determine what a needs. Plugging into the differential equation gives the second derivative of yp is equal to 25 ae raised to 5t minus 4 times the first derivative of yp, which is 5ae raised to 5t minus 12 times the value of yp, which is ae raised to 5t equals 3e raised to 5t. With this, we'll get the value of negative 7 ae raised to 5t equals 3e raised to 5t. In this equation, we can cancel out e raised to 5t, getting the value of negative 7a equals 3. Then, the value of a will be equal to negative 3 over 7. This time, we found the value of our coefficient. So, our particular solution to the differential equation is then yp of t equals negative 3 over 7 e raised to 5t. Example number 2. Find a particular solution for the following differential equation. Y double prime minus 4y prime minus 12y equals sine of 2t. For example number 2, the given is y double prime minus 4y prime minus 12y equals sine of 2t. Now let's take our experience from the first example and apply that here. The first example had an exponential function in the g of t, and our guess was an exponential. The differential equation has a sign, so let's try the following guess for the particular solution, which is yp of t equals a sine of 2t. Differentiating and plugging into the differential equation gives the value of the second derivative of yp of t is negative 4a sine of 2t minus 4 times the first derivative of yp of t, which is 2a cosine of 2t, minus 12 times the value of yp of t, which is a sine of 2t, equals sine of 2t. Collecting like terms yields negative 16a sine of 2t minus 8a cosine of 2t equals sine of 2t. We need to pick a so that we get the same function on both sides of the equal sign. This means that the coefficients of the sines and cosines must be equal, or cosine of 2t is equal to negative 8a equals 0. So the value of our a is equal to 0. For sine of 2t, we have negative 16a equals 1. Therefore, our value of a is equal to negative 1 over 16. We have noticed two things. First, since there is no cosine on the right-hand side, this means that the coefficient must be 0 on that side. More importantly, we have a serious problem here. In order for the cosine to drop out, as it must, in order for the guess to satisfy the differential equation, we need to set a equals 0. But if a equals to 0, the sign will also drop out, and that can't happen. Likewise, choosing a to keep the sign around will also keep the cosine around. What this means is that our initial guess was wrong. If we get multiple values of the same constant or are unable to find the value of a constant, then we have guessed wrong. On the other hand, it is a nice aspect of this method that when we guess wrong, our work will often suggest a fix. In this case, the problem was the cosine that cropped up. So to counter this, let's add a cosine to our guess. And our new guess is yp of t equals a cosine of 2t plus b sine of 2t. Plugging this into the differential equation and collecting like terms gives negative 4a cosine 2t minus 4b sine 2t minus 4 times negative 2a sine of 2t plus 2b cosine of 2t minus 12 times a cosine of 2t plus b sine of 2t equals sine of 2t. Again, combining like terms gives negative 4a minus 8b minus 12a times cosine 2t plus negative 4b plus 8a minus 12b times sine of 2t equals sine of 2t. With this equation, we'll get negative 16a minus 8b times cosine 2t plus 8a minus 16b times cosine times sine 2t equals sine 2t. Now set the coefficients equal. For cosine 2t, we'll have negative 16a. Cosine 2t will have negative 16a minus 8b equals 0. And for sine 2t, we'll have 8a minus 16b equals 1. Solving this system gives us, for the value of a, we have 1 over 40 and b negative 1 over 20. We found constants at this time and we guessed it correctly. A particular solution to the differential equation is then yp of t equals 1 over 40 cosine 2t minus 1 over 20 sine of 2t. Variation of parameters. Variation of parameters is a general method for finding a particular solution of a differential equation by replacing the constants in the solution of a related homogeneous equation by functions and determining these functions so that the original differential equation will be satisfied. In methods of variation of parameters, we must consider the form ay double prime plus by prime plus cy equals g of x, where g of x is not equal to 0. The general solution is y equals yc plus yp, where yc is based on homogeneous equation and yp is using WRONSKIAN method based on the form of yc. Example number 1. Find a general solution to the differential equation. 2y double prime plus 18y equals 6 tangent of 3t. So our given is 2y double prime plus 18y equals 6 tangent of 3t. First, since the formula for variation of parameters requires a coefficient of a 1 in front of the second derivative, let's take care of that before we forget. The differential equation that we'll actually be solving is y double prime plus 9y equals 3 tangent of 3t. We will leave it to verify that the complementary solution for this differential equation is y sub c of t equals c1 cosine of pt plus c2 sine of 3t. So we will have for y1 of t, y1 of t equals cosine of 3t. For y2 of t, equals sine of 3t. The WRONSKIAN of these two functions is w equals cosine 3 of t giving this a value of sine of 3t. For the next function, we have negative 3 sine of 3t. And with this, we'll have 3 cosine of 3t equals getting the determinant, we will have 3 cosine squared of 3t plus 3 sine squared 3 of 3t equals 3. For our particular solution, we'll have yp of t, yp of t equals negative cosine 3 of t times the integral of 3 sine of 3t tangent 3t all over 3 dt plus sine 3 of t times the integral of 3 cosine 3 of t tangent 3 of t all over 3 dt. Therefore, we can simplify this and it will become negative cosine 3 of t. Simplifying 3 sine of 3t tangent 3t all over 3, it will become sine squared three of t over cosine 3 of t dt plus sine 3t times the integral of sine 3t dt. Simplifying these functions using trigonometric identities, we will have negative cosine 3 of t times the integral of 1 minus cosine squared times 3 of t over cosine 3 of t dt. 3 of t dt plus sine 3 of t times the integral of sine 3t dt. Therefore, we need to simplify again the equation 1 minus cosine squared 3 of t over cosine 3 of t, giving us negative cosine 3 of t times the integral of secant 3 of t minus cosine 3 of t dt plus sine 3 of t times the integral of sine 3t dt. Therefore, we will have negative cosine 3 of t over 3. Then, getting the integral of secant 3t minus cosine 3 of t giving us the equation ln secant 3 of t plus tangent 3 of t minus sine 3 of t plus the integral of sine 3 of t dt, giving us sine 3 of t over 3 times negative cosine 3 of t. With this equation, we'll have negative cosine 3 of t negative cosine 3 of t over 3 ln secant 3 of t plus tangent 3 of t. Then the general solution for this is y of t equals C1 cosine 3 of t plus C2 sine 3 of t minus cosine 3 of t over 3 ln secant 3 of t plus tangent 3 of t. Example 2. Find a general solution to the differential equation ty double prime minus t plus 1 y prime plus y equals t squared. So our given is ty double prime minus the quantity of t plus 1 times y prime plus y equals t squared, given that y1 of t equals e raised to t and y2 of t equals y2 of t equals t plus 1. It is a form of fundamental set of solutions for the homogeneous differential equation. So, as with the first example, we need first to divide out this by a t. So with this, we'll have the equation y double prime minus the quantity of 1 plus 1 over t times y prime plus 1 over t y equals t. The WRONSKIAN for the fundamental set of solution is W equals e raised to t gives us t plus 1, and for e raised to t gives us the value of 1. And getting their determinant will give us the equation e raised to t minus e raised to t times the quantity of t plus 1 equals t plus 1 equals negative te raised to t. For our particular solution, we'll have yp of t equals negative e raised to t times the integral of the quantity of t plus 1 times t over negative te raised to t dt plus the quantity of t plus 1 times the integral of e raised to t of t over negative t e raised to t dt. Getting the integral of the equation, we will have e raised to t times the integral of the quantity of t plus 1 e raised to negative t dt minus the quantity of t plus 1 times the integral of dt. Then we will have e raised to t times the quantity of negative e raised to negative t times t plus 2 minus the quantity of t plus 1 times t. Then we will have negative t squared minus 2t minus 2. Then the general solution for this differential equation is y of t equals general solution y of t equals c1 e raised to t plus C2 times the quantity of t plus 1 minus t squared minus 2t minus 2. That would be all for our lesson 7. Thank you for watching.